Get started. Any questions before we get started? Any questions before we get started? I'm on.
Yes. When's the last day we took the test?
Yesterday.
No.
No, sorry. No, I think is it tomorrow?
Thursday.
Thursday, yeah.
Okay.
But make sure you have it in there, otherwise, if you're not scheduled to take it, then you still won't be able to. Make sure there's a slot for you to take, okay? Anything else? Did you have a question?
I have a question from not from Khalid.
Okay. All right, let's get into gases. All right, kinetic molecular theory. Basically, this kind of tells why gases do what they do. And it's a theory. Why is it a theory? We still can't see them, right? But based on what we do know about every other thing, this is how it should go. Okay? So the first point is gas molecules are constantly moving at random. Constant. So they go until they hit something, and then they change direction, just like anything, right?
Moving around
Yep, they're just always moving around.
like oxygen.
Yeah, any gas. Okay, the next point is the space in between the gas particles is much, much, much greater than the space that the gas particles take up themselves. So when we talk about the volume, we're just interested in the volume of the actual space. You got something? Sorry. So the amount of space occupied by the gas by the gas molecule itself
Oxygen.
is much, much smaller. Where? The amount of space occupied by the gas molecule is much, much smaller than the space between molecules.
Much more.
So we're talking about three-dimensional space. This is called what? Starts with a V. Volume, right? So this is the volume. When we consider the volume of gas, it's just the space that the gas is in, okay?
Space between molecules.
Molecules. Any questions so far? Okay. Okay, we talked about intermolecular forces. For gases, they're basically negligible. Now, why is that?
There's none of them around.
Yeah, they're so far apart, they don't come in contact. Now, when they do, it's just for a brief instant, right?
They form liquid.
So, although there are intermolecular forces are, so especially for a gas, for a covalent compound, are very weak, right? And if they're not staying together, it's basically not there. Does that make sense to everybody? So gas intermolecular forces are negligible. So there's no attractive or repulsive forces between them. Not any to worry about anyway. And as the temperature of gas increases, what else increases?
The space between parts.
The speed. So they, as things heat up, they go faster and faster and faster. And what kind of energy are we talking about there? Kinetic energy, energy of motion, right? So kinetic energy, and we'll just say the average kinetic energy, because if it's a certain speed, certain temperature, a certain amount of energy, does that mean every molecule has the same speed? What if they're the same size? Still might not, right? So some might have a little bit more energy, some might have a little bit less energy. So we're just talking about the average, and this little bar over the kinetic energy that represents average kinetic energy is proportional to the temperature. So if the temperature goes up, the kinetic energy goes up. That makes sense to everybody? We can go deeper into all this stuff, and we're not. Is that okay? Okay. Collisions of gas molecules are elastic, is the last one. Meaning they hit, they come apart without any loss of energy. What do you think? Is it perfectly elastic? Do they lose any energy? There might be slightly lost, but again, it's negligible. This is the most elastic collision that we know of. Any questions on the kinetic molecular theory? Now, we'll talk about this as we move on. But this is basically our understanding of what gases do. Any questions on any one of those, of why they do what they do? Because there will be a test question on this. Let me think. So I can't remember which one, so we'll just know them all. Okay? And how they apply. So gas molecules are constantly moving at random until they hit into something else, and they undergo a elastic collision, meaning they don't lose any energy, they just hit and bounce off, right? And then they're so far apart, there's so much space in between them that there's negligible intermolecular forces, so no other forces. And the pressure itself of the gas is caused by the molecules running into the walls of the container that they're in. And of course, You increase the temperature, they increase the speed, therefore the kinetic energy. Good? All right, let's talk about pressure. Pressure is a force exerted on an area of space, exerted per unit area of space. Force exerted per unit of area. So P, capital P for pressure equals force over area.
Area or unit of area?
It is over area, but so if we use units, what's the unit of force? Anybody know the SI unit of force? Isaac Newton, right? Okay. Over what's the unit of area? Meters squared. Okay? So that's the SI unit of pressure, and we call that a Pascal. But for some reason, we don't use Pascals in this class. Because when we use, we'll get into that a little bit later. So think of a bed of nails. Anybody ever lay on a bed of nails? Okay. You're okay, right? Because it distributes your weight or the force over a large area. So if you have a huge area dividing by a huge number, our pressure is tiny. It's inversely related. You following? That makes sense in your mind? Okay. But if somebody weighs more, that pressure is going to go up. And that should make sense to us, yeah? But if instead we do a handstand on that bed of nails, good news or bad news? The area gets smaller and smaller and smaller, therefore the pressure gets bigger and bigger and bigger. Good? Don't do handstand, guys. Fortunately for me, I can't. So at sea level, because we're never at sea level, so we talk about sea level stuff all the time, right? Where's sea level? At the ocean? Okay. Anyway, we're not there, unfortunately. But at sea level, then the atmospheric pressure is about 14 psi. It's not exactly 14. And we don't use psi in this class, so I'm not going to have you convert from psi or whatever. What does psi stand for? Just because this is most common. What is it? What? Pounds per square inch. Okay. But still, pounds is a unit of force. Area, inches squared is a unit of area. So although this is a unit of pressure, we use this when we pump up our car tires or bike tires, right? Or basketball or football or whatever.
Pounds per what?
PSI, pounds per square inch, per inches squared.
Inches squared.
Yep. Okay, one that we used when we first come up with the barometer. You guys know what a barometer is? So a barometer is a device, and this is a cartoon image. It's probably not exactly how it is. But you have your mercury kind of sitting in here in this little container. And then you have a tube coming up here. And this mercury rises up into the tube. Well, what pushes it up there? The air pressure pushes down here. And it pushes, and it makes that mercury rise. Well, it rises, so at sea level, it rises 760 millimeters. So we call this 760 millimeters of mercury. They use centimeters of mercury. They also use inches of mercury. We're not going to do that, okay? So for this class, we will use we will use millimeters of mercury because it's a common unit. And then the unit that we mostly use in this class is atmospheric pressure, because we deal with atmosphere, right? And at sea level, the atmospheric pressure is about 1 atm. An atm stands for atmospheric pressure.
One 18.
Uh-huh. And so a conversion factor we need to know, you will be tested on this, is 1 atm is equal to 760 millimeters of mercury. Because we will have to use that conversion factor in some of our problems. And just to give you what it is in pascals, why? Because that's the SI unit of pressure. It's icky, yucky number. 101,325 pascals. And it's a dude's name, so it's capitalized. Okay? Any question on what pressure is? Measured in and conversions, okay? So we're just real simple right now, then we'll get into calculations to figure some of this stuff out. The next one we're going to talk about is volume. We talked a lot about volume, so I'm not going to spend a lot of time on this. Volume is the total space occupied by the gas. When we're talking about gases anyway, right? And what units do we use for volume? Liters. We use liters, we use milliliters, and sometimes we use, especially in your field, we use cc's. What's cc stand for? Cubic centimeters, right? And I think I told you this already. What's the relationship between milliliters and cubic centimeters?
The same.
They're the same. 1 milliliter is the same as 1 centimeter cubed. So if you're given a volume in centimeters cubed, well, just change that to milliliters, right? And then, of course, we know how to go from milliliters to liters, because we will need to know how to do that. Everybody clear with that? Okay. Any questions on volume? Okay, so it's almost like review here, yeah? All right, now let's talk about temperature. We're already familiar with temperature a little bit here. Temperature is, it's the unit directly related to kinetic energy we talked about. But it's measured in what? Kelvin. But we don't have a device that measures in Kelvin, so we always have to convert. Now, does anybody want to know how to convert from Fahrenheit to Celsius? You do? Okay. I'll show you. I might have to look it up. We won't use it in this class, But we use Fahrenheit, right? Here in America, still use Fahrenheit. Why? Because everybody's stuck on it and we don't like change. If we just all change, it's gonna be better, right? But anyway, anybody want me to show you how to convert? Okay, let me make sure I think I have it in my head, but sometimes it's flipped. Because it's a weird little thing. So temperature in degrees Celsius is equal to temperature in Fahrenheit minus 32 multiply 5/9. So there's the formula. Do you want to practice it? Do it. But it's kind of icky, right? We kind of understand maybe why it's 32, right? But why that? Because each increment's just a little bit off, right? One degree Fahrenheit change is different than 1 degree Celsius change. But in Kelvin, Celsius and Kelvin are the same. That's why it's pretty straightforward. The more important one, I think, go to Kelvin is degrees Celsius plus 273.15. And that is on your reference sheet, so you don't have to memorize that. But we're going to be using it quite a bit in this unit, so you'll probably get it stuck in your head, hopefully. Okay. Any questions on either of those? Because I believe we talked about this one anyway, right? Okay. So in this unit, we have to be measured in Kelvin. If we're not, our answers are going to be goofy. And I'll explain why when we get there. All right, so maybe just we have to be able to convert millimeters of mercury to ATM or ATM to millimeters of mercury. Let's do one of each of these. Just so that it's just dimensional analysis. It's just a conversion. So if we have 854 millimeters of mercury, and we want to convert this to ATM. And why do we? Because our formula that we're going to be getting into this unit, it must be an ATM. Well, for the constant that we know, unless you want to learn a bunch of constants. Anybody? Okay. All right, so we start with what we know, 854 millimeters of mercury. What goes on bottom? How many millimeters of mercury? Good, 760 millimeters of mercury to, what goes on top? 1 ATM, that's it. No big deal, right? And we get 1.12 ATM. Good? Let's do one volume just to make sure we got this. We have 453 centimeters cubed, or cc's, and we've got to convert this to liters. How should I write this? What should I start with? 453 what? We could start with cc's. We just change it right over to milliliters because they're the same. Are we good with that? And if you want to convert it, you definitely can. 1 centimeter cubed is the same as 1 milliliter. No big deal, right? Then what goes on bottom? 1,000 milliliters. We use this more than any other prefix in this class, right? Milli to 1 liter. And we get 0.453 liters. Good? (25°C to Kelvin). Somebody tell me what we do. We just add 273.15. That's it. And if we're going from Kelvin to Celsius, what do we do? Subtract 273.15. Okay. So we're going to get 298.15 Kelvin. All right. Did I waste your time, or are we good? Okay. Just a review of the basic conversions we need for this unit. All right, now let's get into the gas laws themselves. Unless you have any questions. Okay. Okay, I don't need you to necessarily know the names of these laws. I'm not going to test you on what law deals with pressure and volume. I'm not gonna test you on that. And it's just named after the guy that come up with it, I guess. So the first one we're gonna go over is Boyle's law. And Boyle's law is the relationship between pressure and volume. That means temperature is constant. So if temperature is constant, this is the formula that we use. So now let's just use our thinker. And maybe we don't, maybe we have a hard time using our thinker and our experiences to come up with something. That's okay. We can just memorize this formula and we got it. So what is the relationship between pressure and volume? What happens to pressure if we increase the volume? What? Gets bigger? So if we take our balloon, for example, or our piston, like in a combustion engine, and we open it up, what happens to pressure in there? It goes down, right? More space for those molecules to move around. So it's inversely related. So we can say pressure is proportional to 1 over the volume. Does that make sense to everybody?
Pressure equal?
Not equal, it's proportional to. But it's not useful if it's not an equation, right? So we'll say, okay, pressure is equal to some constant value, K, times 1 over V. Now what's that constant? We don't need to know what that constant is, but what's constant? Temperature is constant. Okay? So let's solve for the constant by multiplying both sides by volume. And we get our constant is equal to pressure times volume. Or volume times pressure, doesn't matter. Good? So if at a constant temperature, then the product of volume times pressure is always going to be the same. Therefore, we can write an equation. P1 V1 equals P2 V2 equals P3 V3, and so on, right? So this is Boyle's law. So when we're dealing with a situation with constant temperature, we want to calculate pressure volume. We got it, yeah.
What's the difference between P1 and P2 or V1 and P2?
So we can also call it initial pressure times initial volume is equal to final pressure times final volume. This one's just more simple, but same thing. Thanks for asking. We good there? Does that make sense in our mind why that's the formula? And you don't have to derive it. We just derived it here. But now we can just use this. So let's do an example. Am I going too quickly? Too slow? Okay, example. So the pressure of gas in a 600 milliliter cylinder, so that's the volume, is 65 millimeters of mercury. So I'm reading this to you, so you'll be given a story problem. But do you remember how to do story problems or use the problem solving strategy? Write down what you know and what you're looking for. That's all I'm doing as I'm reading this. Good? If the pressure increased to, now the pressure is, so we'll call this P1 and V1, right? So our pressure increased to 385 millimeters of mercury. We want to know what our final volume is at a constant temperature. Anybody scared with this? We feel pretty confident with this basic algebra? Because there's going to be a lot of calculations this unit. But it's simple equations. When I say it gets a little bit more complex, but not much, okay? So we take P1 V1 equals P2 V2. And by the way, it won't tell you which one is P1 P2 or V1 V2. You'll have to just recognize that. Does that make sense how to, though? Whatever you start with, that's your initial case or your case 1. Wherever you're going to, that's our case 2 or our final case. Okay? So we want to solve for V2, so let's multiply both or divide both sides by P2. Are you with me? Or am I just doing the math for you? Can we do this? Okay? And so we get a formula of V2 is equal to P1 V1 all over P2. So we can plug our values in. A lot easier for me anyway, to solve before you plug the numbers in. I would try it both ways, and whatever way you like, use that way. Okay? Just make sure you're careful with units.
Is it P1 V1 is multiply and then divide by P2?
That's right. Yep. So P1, in this case, is 65. Now, guys, a lot of students, when I say a lot, mostly high school, but still some college students, don't want to write all the units. And so they'll just say 65 multiply V1, which is 600, divided by 385. Are we okay in this case not writing the units?
Yeah.
Yeah. Will there be some cases where we're not okay? I would just always write the units. Just like dimensional analysis, guys. Always use dimensional analysis, okay? So 65 millimeters of mercury multiply 600 milliliters divided by 385 millimeters of mercury. What cancels? Millimeters of mercury, leaving us with milliliters, so we know what our answer is measured in. If we just have numbers, we might say centimeters cubed. Well, that's the same thing. We might say liters. What? So we do this and we get our final volume is going to be 101.3 milliliters. Good enough?
Fine, V2.
So now ask yourself, can you do this on your own? If you can't, say something right now. Yeah, he's got.
Can we do another example of that?
Of this one? Yeah. Okay, let's say we have a balloon. Maybe this isn't a good example, but it'll still work. So we have a volume of, let's say, 2.5 liters. And we have a pressure of, I'm just guessing, let's say 1.5 ATMs. Then later at the same temperature, see this is why it's a bad example, because it's not a real one. So we'll take the same balloon, let's say, for some reason or other, then the volume changes to 1.6 liters. Now what's the pressure?
This is P1, P1.
Yeah, so which one is P1, which one is V1?
It doesn't matter.
It doesn't matter as long as you keep the P1 and V1 together, right? This is our first case, and this is our second case. So we call this V1 and P1, this V2 and P2. So it doesn't matter if you flip-flop it. It really doesn't matter because they're equal, right? Is that making sense? Okay. Now, do you want to plug numbers in first this time? Okay. All right, we got P1, V1 equals P2, V2. So let's plug our values in. So P1 is 1.5 ATM. Multiply V1 is 2.5 liters. Equals P2, we don't know, so we'll just leave it as P2. Multiply V2 is 1.6 liters. So now what do we do to solve for P2?
Divided.
Divide by 1.6 liters. What cancels? Liters goes away, leaving us with ATM. So it doesn't matter what unit of pressure we use here. It really doesn't. Just make sure they're the same so that things cancel out. Same with volume. Make sure they're the same. And I don't have the answer for this one, so we got to figure it out. What is it? 2.37? 2.31?
2.3.
Okay, sorry. And units are going to be what? ATM, because that's all we're left with. Does that make sense? Okay. And on the worksheet you picked up, there's some more example problems. Should have just picked one from there, but that's okay. Any other questions on Boyle's Law? Yeah.
Are we gonna go to 3 and 4 in this
What do you mean?
Later on, like values, like cover you like E1, E2, E3.
You could, but either way, if you find pressure and volume of one case, you can find any case, right? But I don't think I'll ask you that.
On workshop, can we do the 0 to 100 minute minute?
The 0.2 liters to milliliters? Yeah. Do you know the conversion from milliliters to liters? Do you know that conversion? And this is one you have to know. So milli to whatever else. So it can be milligrams to grams. It can be milliliters to liters. It can be millimeters to meters. Doesn't matter. What's the conversion factor? 1,000 of these is equal to one of those. Does that make sense? And so for this one right here, 0.2 liters, we're going to put 1 liter on the bottom, 1,000 milliliters on top. And we got 200 milliliters. Good? So basic dimensional analysis. And I won't give you that conversion factor. You need to know it. Same with these conversion factors right here. Somewhere. Right here. You need to know this. I won't give... In fact, is that one's... Maybe that one is on our reference sheet. It is?
Yeah.
Okay. That one is on our reference sheet. So we're good there. But our metric to metric, we need to know. Any other questions before we move on?
And another was K to C.
So we did one like that. If you're going Kelvin, so we're going to use this formula. Temperature in Kelvin is equal to temperature in degrees Celsius plus 273.15. So are we going from K to C or C to K? Which one?
It's K to C.
Okay. So we know we have 2,950 Kelvin, and we want to know what it is in Celsius, right? We'll just plug it in. We're looking for degrees Celsius. So what do we do to solve for this? You tell me.
Minus.
Yeah, that's it. And then we're done. That is it.
Minus.
Minus 273.15 to both sides, and that's going to give us our temperature in degrees Celsius. Good? Yeah. All right, you ready for the next law? Okay, the next one is called, there's a few different names, but I'll just give you this one. Gay-Lussac law. And this one is the relationship between
K what?
Gay-Lussac. Pressure and temperature. So let's just think about this. What is the relationship between pressure and temperature? If we increase the temperature, what happens to the pressure, would you think? Increases, right? They're directly related. If we make the particles move faster and faster and faster, they're going to be pushing. So kind of like if we have a balloon. You blow up a balloon and you put it in hot water. What's going to happen? It's going to expand. It's gonna push it out. So when we use Gay-Lussac's law, we're talking about constant volume. So I guess that's not the balloon case, right? All right, so pressure is directly proportional to temperature. So if we want an equation, pressure is equal to what? Some constant K times temperature. Making sense? Okay. Now let's find out what that K is. What do? Divide temperature to both sides, and we get K is equal to pressure divided by temperature. So the ratio of pressure and temperature is always going to be the same when volume is constant. So what's our formula? P1 over T1 equals P2 over T2. You following? Just like the other one, the other one just didn't have a fraction, right? But can we still do the algebra? Okay. So let's do an example. Okay, the pressure inside a basketball in the morning is at 10 degrees, sorry, that's not the pressure. The pressure is 720 millimeters of mercury, and in the morning it's a little cooler. So the temperature is 10 degrees Celsius. Then it's been sitting in the sun all day long. So we want to know, well, what is the pressure? And it's been in the sun all day long, so the temperature increases to 34 degrees. Okay, the very first thing we have to do before we do anything else is convert to Kelvin. We must convert to Kelvin, guys. We won't get the same answer either way. We will not. Okay? So 10 degrees in Kelvin is 283.15. Y'all with me? And 34 degrees is 307.15. All right, now we can worry about calculating this. So just make sure you always convert to Kelvin first. And if we're just doing this to get done, we might forget that step. So slow down. Always go to Kelvin. Which way did you like better? Putting the numbers in first or calculating first? No opinion? Either way? Okay. If no opinion, what would you say? Put the numbers in first? Okay. Did you try it the other way? Why don't you try it the other way? I'm not saying you have to like it better. I'm not. Okay? If you decide, you know what, I've tried this, I tried to like it, but I just don't like it, that's fine. No problem. Okay? But the reason I'm saying this, because I remember when I learned this, not this particular thing, but the guy says, it's way easier to solve first. I'm like, what? That's backwards from what I did it. I didn't like it at first. I tried it a few times, like, hold on a sec, I like it better. So be willing to change, because sometimes change will be good, right? But if you still don't like it, no big deal. Okay? All right, so we got P1 over T1 equals P2 over T2, and we're solving for, ooh, yeah, we better put these 1, 1, 2, 2, right? So we're solving for P2, therefore we do what? How do we multiply by T2 to both sides? Plug our values in. 34, is that right?
Nope, 307.
Ooh, good. Make sure we use Kelvin. Real easy to just hurry up and do it. Multiplied pressure one is 720 millimeters of mercury divided by 283.15 Kelvin. Kelvin goes away, so our answer is going to be measured in millimeters of mercury. If the test asks you to put it in ATM, then you'd have to convert it to ATM later, right? Or before, doesn't matter. But I'd rather later, because then you only have to convert one thing. Well, in this case, still only one thing. All right, we do this and we get our final pressure is 781 millimeters of mercury. We good? Any questions on Gay-Lussac law? Yeah.
So in the guide for the exam 4, the point 4 is the one that we are doing right now.
So that the study guide, that's for this new unit, yes.
And we have the point 4. So that's the big doing right now. It's because the formula is something different. It's volume.
Which number 4? Yeah, we didn't do that one yet.
Okay.
Yeah, we'll get there. Any other questions? Okay, let's move on to Charles' law. And Charles' law is the relationship between volume and temperature. Okay, so we get our balloon. This is the balloon example. We get our balloon and we heat it up. What's going to happen? The volume gets bigger. So what's the relationship between volume and temperature? Yeah. Inversely or directly? If we increase the temperature, what happens to our balloon? It pushes them out, right? So they're directly related. So volume is directly proportional to temperature. Okay, here's what I want you to do. Come up with Charles' law. Go. Try it. Just like we did it two times, try it. Did we get it?
I believe it's the same. So
V1 over T1 equals V2 over T2. Is that what you said? That right? Should we try it or yeah, let's try it. So this is V equals some K constant times T, right? Is that what we did? And then we divide both sides by T. Yeah. So volume over temperature is always going to be a constant. Good. So in the worst case scenario, you can just think about what's the relationship between this, and you can come up with it, right? I'll show you a best case scenario a little bit later. Okay? Because if you look at your reference sheet, do you get these formulas? You do not. But I will show you how it is on there. There is one formula that's on there. I'll show you when we get there. Okay? That it's related to all these. In fact, that's how we get to that one. Okay. Let's do another example. So we have a hot air balloon. Anybody ever fly in a hot air balloon? Oh, I almost did one time, and the weather was bad. And I never tried it ever since. Like, I don't know. Anybody would dare to do that? It would be fun, but yeah, there's always a risk, right? It's kind of like skydiving. It's like, I don't know if I want to do that, but but it would be fun as heck, right? If you know you wouldn't get hurt, okay, that's not chemistry. All right, so let's talk about a hot air balloon. We have a hot air balloon has a volume of 955 liters at a temperature of 56 degrees Celsius. And we want to know, well, what's the temperature when the volume is 875 liters? Should we plug the numbers first in this time?
when I solve for Kelvin.
Oh, yeah. Got to solve for Kelvin first, right? So what's 56 in Kelvin?
329.
329.15 Kelvin. Good. Anybody still want to plug numbers in to solve? We can. Definitely can. No big deal. You want to do that, Mariana? Okay.
56
So 56 degrees is the same as 329.15 Kelvin. And we got to use Kelvin. So V1 over T1 equals V2 over T2. So we plug our values in, and so we're going to say this is our volume 1 and temperature 1, volume 2 and temperature 2. So V1 is 955 liters. Temperature 1 is 329.15 Kelvin. Equals volume 2 is 875 liters over T2. Oh, is it 75? Yeah, 75. Okay, so what do? Oh, that darn variable's on the bottom. We could just flip both sides. That's probably the easiest. One thing that people do is we cross multiply. We could do that too. We can get rid of all the fractions altogether. You want to do that? Okay. So we multiply that over there and multiply this over here. Do you guys understand why we can do that?
I never have.
Okay. And it seems like in a math class they just tell you all these little tricks and stuff, but it's just all following the laws of algebra. If you understand the laws of algebra, they work no matter what, with letters, with numbers, all the same.
But the
Okay.
other, two will not cancel each other.
So they didn't cancel. So cross multiply is what we call it. But here's, I'm going to do it the good old fashioned way and show you why it works. So normally we want to multiply those together, right? Well, to get rid of this fraction, we just multiply by t2, is that right? Oh, there it goes. Now it's up there multiplying by that guy. And then that's on the bottom, so we'll multiply both sides by 329.15, and that goes away. Do that to both sides, 329.15 Kelvin, and it multiplies there. So that's why you can just cross multiply. You with me?
Mm-hmm.
Just know that that's not the same as cross cancel. That's why I don't like using that term, but it's not the same thing. So we got 955 liters multiply T2 equals 875 liters multiply 329.15 Kelvin. Do you want to simplify first?
Yes.
Okay, we can, except for what do we do with those? Leave them there. They didn't cancel, so don't cancel them. So what's 875 multiplied 329.15? Something. I didn't do it this way in my notes, so you tell me.
288,006.
So 2,886 or 288,006?
288,006.
Okay,
0.25.
good enough. Don't round until the end, right? This is why it's an advantage of solving first, because then you don't have to worry about not rounding. You just plug your numbers in and enter. That's your final answer. You can round. But here this isn't our final answer, so don't round yet. We still have liters Kelvin, right? Equals 955 liters times T2. Now, to solve for T2, what do? I knew you guys said that in your mind, right? Okay. Can we do this? Or am I just doing it for you on this case? Okay. Divided by 955 liters. Liters goes away. We're left with Kelvin. That's good. So T2 is going to be 301.6 Kelvin. Did that kind of show you why it's better to solve with variables first? If you didn't, no big deal. I'm not going to condemn you if you like it this way better. Promise. Okay? But that just seems a little bit messy to me. And a lot of different steps. When you just solve with variables, then you just plug and calculate and it's done. Yeah.
Do we be answering kelvins or do we need to change to Celsius?
That's a good question. So on the test, if the answers are measured in degrees Celsius, then yes, you have to, right? But if they're in Kelvin, you can just leave it in Kelvin. But generally, we would probably want to put it in Celsius, right? Because we don't even understand Celsius very well, probably, right? We want it in Fahrenheit if we want to understand what it is, right? If we want to relate it, well, I don't even know how hot that is, right? So in this case, yeah, you might want to, but for this class, you just go whatever they're asking. Andrew.
Still trying to wrap my head around the formulas because I couldn't figure out what Charles' law was. So, like, for example, the Gay-Lussac law, like, before we got to the final formula, it was P equals K times T.
Uh-huh.
Why is it that we're multiplying K Kelvin
It's not K Kelvin. It's a constant.
Okay, I guess that's what.
It's that's why it was lowercase k.
Okay.
And all we used that for was to derive what the formula is. Am I going to ask you to derive the formula? I won't. All you need is that formula, which is, so in this case, here's Charles' law formula. The V1 over T1 equals V2 over T2. And you got the Gay-Lussac law, which is P1 over T1 equals P2 over T2. And Boyle's law, which is P1 V1 equals P2 V2. That's all you really need.
So we could also say V1 over T1 equals P because pressure is the constant. Well, or K, I guess. I guess I don't get why we use K as the constant instead of just putting like pressure or whatever the constant is in there. But
Okay.
okay, just checking.
When we combine them all together, it might click.
Okay.
We'll see.
Great.
Okay. There's one more individual law, and that's the relationship between volume and the amount of gas, or number of moles. Okay? And so this is called Avogadro's law. And this is the relationship between volume and N, where N is the number of moles. Did we talk about that yet in this class? I don't think so. N being the number of moles. We'll use it a few other times after this unit. So N is the number of moles. All right, now let's think about this. If we have a balloon, has a certain number of moles of carbon dioxide we blew in it, right? What if we put more in it? What's going to happen to that volume?
Increase.
So what's the relationship between volume and the number of moles?
Direct.
Directly related. Does that make sense to everybody?
We're putting more moles of carbon dioxide in that.
Yeah. Okay. Now, I could come up with a formula just the same. But the cool thing with gases, and this is really Avogadro's law, the cool thing with gases is all gases behave the same. Doesn't matter if you're dealing with oxygen gas, propane gas, or any other type of gas. If it's a gas, it's going to behave the exact same way. So when we deal with Avogadro's law, we're talking about constant temperature and pressure. So if the temperature stays constant, the pressure stays constant, then this is what happens. And we kind of know that with a simple balloon, right? So at constant at standard temperature and pressure, we call STP, standard temperature and pressure. Standard temperature is 0 degrees Celsius. Why is that standard? Because it's mostly 0 degrees Celsius everywhere, right? No. Yeah. So why do that? I don't know. Okay, so this is just this is equal to 273.15 Kelvin. And standard pressure is just 1 ATM, 1 atmospheric pressure. You will need to know that for the exam. Okay, so we'll do an example where we, like, yeah. So when we have STP conditions, and it's only for gases, guys. If we're talking about solids or liquids, none of these laws work. We have to be dealing with gases only, okay? So when we're at a condition of STP, then 1 mole of any gas is equal to 22.4 liters of that gas. All right. So that's a nice condition if we're in that condition. If we're not in that condition, then 1 mole is not equal to 22.4 liters.
Is it? No, it wouldn't. Okay.
Does that make sense? So it's a one case thing. Can we find out how many liters we have in every temperature? We could, but who wants to do that? Too many, right? So let's do an example here. And we'll do a couple examples. First, we'll just, like the main reason why we're going over this is to help you to understand all gases behave the same. So at 35 degrees Celsius and a pressure of 456 millimeters of mercury, so that's going to stay the same. I want to know which has more volume, 1 mole of oxygen gas or 1 mole of propanol gas. Which one has which one has more volume?
Wouldn't they be the same?
They're exactly the same. 1 mole of any gas has the same volume at the same temperature and the same pressure. Okay? So we don't know what that volume is here. It's not 22.4. And why is it not? Because we're not at standard temperature and pressure. Are you with me? So we can probably, if we have enough information, we could probably figure out what that volume is. And then it's the same for all gases. Doesn't matter what kind of gas it is. Okay? So let's do another example where we have to use the 22.4. Okay? Let's see, am I going to get there? No, so let me just do one here.
Could you describe why they're the same volume again?
Yeah, because all gases behave the same way. Doesn't matter what the, if it, yeah. Mm-hmm. At the same temperature and pressure anyway, right? If the pressure changes or the temperature changes, then it's going to be different. But, so if we have, let's say, we have N2 plus O2, let's do H2. Gives us NH3. And we have 3 grams, let's do 3.5 liters of nitrogen gas at STP. I want to know how much hydrogen gas is needed. How many grams of hydrogen gas is needed? No, not grams. We'll just do liters. Is needed to completely react with nitrogen gas. What does this look like? Stoichiometry. We good at that yet? We need to get there because we're going to continue to use it for the rest of the semester. I know there's only 2 units left, but we're still going to. In the last unit, we're going to use it quite a bit. And don't freak out about it. If you have a hard time knowing what to do, what do you look at? Mole roadmap. And you're given that map, let's use it. Hopefully by the time we get to the end, you're good at it. And we could just use it. And we could just convert. It's just dimensional analysis. Okay? All right. So we're going to start. Where do you start with stoichiometry? Yeah, we've got to have a balanced equation, otherwise we're wasting our time. Okay, so we're going to put a 2 here and a 3 here, and then we're good? All right, now what? Start with what we know. Don't start with what you don't know, right? And we're going to try to get the liters of hydrogen gas. That's how we know we're done. That's really all the process is. So 3.5 liters of N2 gas. Okay, we got to go to hydrogen gas. And this one is not on our mole roadmap. How do we go? What do we go? What do we want to get to before we can go to another substance? Moles. So can we go from liters to moles directly? Since it's at STP, we can. Okay? So we want liters of N2 to be on bottom and moles of N2 to be on top. Is everybody okay with that? Okay? If we have 1 mole of N2, do we know the volume at STP? 22.4 liters. So you're going to need to know that value. Make sure you know this right here. That's for the test. Okay? Have that on your little reference card if you have to. Okay? Now we have moles of N2. We're not at liters of H2, so we keep going. Do we want moles of N2 on our answer? No, so where does it go? On the bottom. Moles of N2, and now that we're at moles, look at our mole roadmap, and where can we go? Moles of what we're looking for. Yeah. And what's the ratio? 3 to 1. Y'all with me? Get those from the coefficients of our balanced equation. Okay? So moles of N2 go away. We have moles of H2. We're not there yet, so we keep going. And what do we do? 1 mole of H2. 22.4 liters of H2. Do we see this? Are those going to cancel out anyway? It's kind of like what? 6.022 times 10 to 23, right? Okay. So if we're dealing with gases, then we could just kind of avoid that, right? But anyway, you don't have to. You can do it exactly the way we did here. It'll still come out in the end.
Yeah, let's see what is the end.
What?
What is the end?
Oh, we're there now. What's the answer? I have to use our calculator. 2.5? 10.5 liters of hydrogen gas.
Are we gonna have to figure this out, not
No. Nope. You might be asked a question like I asked you earlier, which one has more volume? What if I said 1 mole of oxygen and a half of mole of hydrogen? Which one has more volume? 1 mole, right? Because it's more moles. Doesn't matter what gas it is, they all behave the same way. Okay? Are we okay with that? Any questions before we move on? Yeah, Andrew.
So, so if two gases are not at standard, are they still the same? No.
This is, so if it's the same amount of moles or same amount of gas, then they do have the same volume. But we only know what that volume is at standard temperature and pressure. 22.4 liters.
Or at equal temperature and volume?
Yeah, if it's the same, yeah, if they're both gases are at the same temperature and same pressure,
Everything's the same.
if they have the same number of moles.
Right.
Or the same volume. Yep. Good? So you can think of it as another conversion factor. But that's at STP only. So you have to look for that. Okay?
So like a disproportionate number of chemical labs at sea level to counteract any differences of pressure?
Say that again?
So like, are there more like chemistry or like the science labs like at sea level across the world to make all of this easier?
I don't know.
Right?
Yeah, because it's never going to be a sea level in here, is it?
No. I mean, we're like 20% less.
Yeah. Same thing with the freezing point or melting point of water. It's only 0 degrees at sea level. Same with boiling point of water. It's only 100 degrees at sea level. Really, around in here, it's probably around 98 degrees is where it starts to boil, right? So, and so why is it good to know that stuff? So that we can make predictions. Are our predictions ever going to be 100% right on? Probably not. Probably never. But it helps us get close. And if we're close, we have less waste. Less waste means we make more money. I know it's not all about money, but we kind of like it, right? All right. Any other questions? Should we take a break? All right. Sorry, 10 minutes later.
I answered my own question, and NASA at least has a significant portion of the infrastructure at sea level.
Really?
Yeah.
There you go. Cool, thanks. Thanks for sharing. Thanks for checking it out.
You're welcome.
Uh-huh.
For the extra credit, can we still work on it, or?
Yeah. Just don't push it out forever.
No, it's because I know for the first one, it closed, and then I looked back and it's open again. It's all that.
Did it close, or did it just say it's due?
It says due, but
Okay,
when I
that
went,
doesn't mean it's closed.
okay, because I went back and was gonna turn it in, and it didn't let me.
Oh, but now it does?
Mhm.
Because I didn't do anything.
Okay.
So,
I don't know. And same for this extra credit for the ice cream one.
uh-huh.
can I do a different way instead of like nitrate and
I
it's just
think
like
so.
ice because it's just like with nitrogen.
I
don't know what to
I
do.
believe, did
Dry
it say it
ice.
have to be nitrogen gas? Liquid nitrogen?
I think it was something like.
So you're gonna make it with ice?
Because like I know how to do like with ice and salt that way, but I don't know where to get dry ice or the other stuff that I was asking for.
If,
Or going to a store, it is kind of a little expensive.
okay, yeah, well, yeah, I think that'd be okay, and just, and, cause really, we're just talking about the transfer of energy here, right?
Let me see.
You can make ice cream using an ice cream maker, or, yeah, you can,
Yeah, just
Yeah.
with the, okay.
Yep.
I was just wondering about that.
so,
Okay,
yeah.
so for this. Lines, section, what it does, how do I know? This is my question on this one. I don't understand what does it mean that
Okay,
it is,
so now to turn the spectator ions in a precipitation reaction and an acid-base reaction. Just right here. Just so I don't forget to push record on that again.
I can bring my pencil. Maybe to our review.
Gonna get started again. Any questions with any of the individual gas laws? All right, let's put them all together. So we have P1V1 equals P2V2. We also have P1 over T1 equals P2 over T2. And we have V1 over T1 equals V2 over T2. Can we combine all of these into one equation? And Angie is kind of talking about this a little bit. Can we just put a V in there as a constant? Yes, we can. Okay? So if we do this, we say P1 V1 over T1 equals P2 V2 over T2. Can you all see that?
Would you ever like mix that up, like put the P on top and the V on bottom?
No, you got to have it this way.
Okay.
And here's why. What's the relationship between pressure and temperature?
As one, well, as temperature goes up, pressure is gonna go up.
So we look in here, yeah, there it is. P1 over T1, it's still there. That equation is still there, right? Pressure and volume, that equation is still there. And this one right here, that equation is also still there. Are you given this formula on your reference sheet? Nope. I'm going to show you one more formula eventually. And I'll kind of show you how, if all else fails, just write that equation. You got all four of them, right? Unless you don't have a reference card. But I'll show you how to do it if you don't, okay? So this is called the combined gas law. Combines all of them together, except for Avogadro's. We'll do one more equation, one more formula that puts that into it. Are we good? Okay, let's do an example using this formula. So if we have 3.50 liters of gas collected at 25 degrees Celsius and a pressure of 745 millimeters of mercury. I want to know, what is the volume at STP? Okay, let's label everything. What is this 3.50 liters? What does that represent? Volume 1 or volume 2? Yeah, we start with that one, right? So we know V1 is equal to 3.5 liters. What's 25 degrees Celsius? That's temperature 1. Let's change that to Kelvin, which is 298.15 Kelvin. Y'all with me? And what's this 745 millimeters of mercury? Pressure 1. Are we good? So we have the initial case, and we're looking for the final volume, right? Do we know, so we're looking for V2. Do we know T2? What is it? It's 273.15. It is at STP, standard temperature and pressure. Temperature is 0 degrees Celsius or 273.15 Kelvin. Y'all with me? And pressure is 7. Since this is dealing with millimeters of mercury, we also have to be dealing with millimeters of mercury. If this was an ATM, we could just say it's 1 ATM, right? So we know the pressure is, for standard temperature and pressure, is 1 ATM. And 1 ATM is the same as 760 millimeters of mercury. You following me there? But if you're using dimensional analysis and units don't cancel out, you know you messed up somewhere. And you know you need to change that, right? So always, always, always use units. They're going to save your butt every time. Okay?
So, I don't understand the last one, the 760.
760? 1 ATM is the pressure at standard temperature and pressure, right? And 1 ATM is equal to 760 millimeters of mercury. And this is also on your reference sheet, so you don't have to write that on your card, but you have to know how to use it. Okay? And if it wasn't standard temperature pressure, it was a 1.2 ATM, now you just have to convert it, right? You with me? Okay. So now we have our initial case, our final case, and we only have one unknown, so we can use that formula, right? So you got P1 V1 over T1 is equal to P2 V2 over T2, and we're solving for V2, so is this, how many steps do we have to do to solve this? We could do it in just one step. If I multiply both sides by T2, right, and divide both sides by P2, that goes away and that goes away. You with me? So multiply this same thing on both sides, T2 over P2, and I get my volume 2 is equal to T2 times P1 times V1 all over P2 times T1. And now I can just plug my values in. Don't forget the units, so you can know if they do cancel out or not. And that's it. So let's do that. So T2 is 273.15 Kelvin. P1 is 745 millimeters of mercury. And V1 is 3.5 liters. all over. P2 is 760 millimeters of mercury. And T1 is 298.15 Kelvin. You with me? So now we just multiply and divide. Does it matter the order we multiply and divide in? It doesn't. And we'll get V2 is equal to 3.14 liters. So pi liters, right? We don't have to call it pi liters. How we feeling?
Feeling tired.
Feeling like we can do this on all these? So there's 4 formulas I gave you, yeah? And basically, if you know this combined gas law, that really shows all of the formulas. So if we have this formula here, if we know that, I'm going to get rid of all this stuff for a minute. All right, so if we know that volume is not involved or is kept constant, we can just delete that. And then we have the formula that we need. Uh-oh. Oh, took it all. So V1, V2. If we know pressure is constant, we get rid of it, we've got a formula. And if temperature is constant, we get rid of the temperature, and we got the formula. Questions? But if we have other things, maybe this is not the formula that we use. Okay? Don't just go to this and, oh, I can do this. I can just get rid of these, and I get it, right? You have to have 2 cases to use this formula. Okay? Any questions so far? All right, let's look at our. Do you want to practice some on your own before we move on? Okay. So the first section in our worksheet is just basic conversions. I'll let you do that if you want. But the second section is we're using the individual gas laws to solve the 4 problems down here. And then we use the combined gas law in section 3. Let me know if you want to try some together on the board. And I will post the answers up here so you can know if you're doing it right. But if you can't do these on your own, you won't be able to for the exam either. So practice this. On Thursday? That's okay. Everybody else gets till Thursday, so yeah.
Did chapter 6 yesterday, and I'm gonna do chapter 7 today, but I have some questions on chapter 6 while I was doing homework.
Okay.
I think I could run through them out.
Yeah, Yeah, you want to stay after class and, And ask?
After class, I can ask.
okay.
Are we doing question two?
So which one?
Are we doing this one?
So, yeah, we could do one from section 2 or section 3, yep.
Okay.
Section 3 is just one problem, really, but, so section 3 kind of goes over everything. And then section 2 is just a single individual gas law. In fact, we can be done for today if you guys, if that's probably enough.
I think that's enough.
Is that enough information today? All right. So keep practicing, or if you got the stuff, you feel confident, yeah, we're done. Thursday? Uh-huh. Yeah.
You see this, but the problem when I said an example.
So get real good at it. Do you have a question?
Does it matter if we do Kelvin or Celsius?
Yes, it does. And you must do, always do Kelvin. Always in Kelvin. Try it both ways, you'll get a different number.
Yeah, I was looking at the rates and I was like,
You have to use Kelvin. You get numbers if you use different pressures too. But that's okay, you'll just have a different unit.
For this, if you can put the formula, some code formula, it's not something huge like chemical reaction. Chemical reactions or chemical 12 levels.
Sorry, what do you
Like
say?
chemical reactions, chemical equations are a little complicated. This is the formula,
Yeah.
and equates easy to answer.
Okay. Yeah. Yeah. Not too bad.
Like, I will show you my case.
Okay.
Sorry.
lab this morning. Took a
Just take Celsius and add 203.15.
So that is the right.
But, in this case, all we're doing, we have a temperature, all we're doing is put that temperature, just take that temperature and add 203.
Okay, so that's.
Oh, sorry.
Any questions on any of these? Okay, like I said before, if we're done, we're done. And, yeah.
So I got the correct answer for section 3,
Uh-huh.
but I guess just conceptually, why does the volume, I guess it increases when both the pressure and the temperature?
Okay.
Is that, if I remember right?
So pressure goes down,
Mm-hmm.
so therefore,
And temperature goes down as well.
well, how are they related? How is volume related with pressure?
Inversely.
Okay.
But
So,
it's related directly with temperature. I guess just a mix of.
not exactly. When it's in one situation, it is. But when we're dealing with two different situations, that's when that's why it looks that way. No, great question.